Hey everyone, I'm here at the Bozeman, Montana airport with a demonstration of our NVIDIA Jetson Nano-based mask detection smart camera. The camera is set up to count people walking by and determine what percentage of them are wearing masks. In this demo, I'll explain what MaskCam is and show you how it works. Right now, I've got MaskCam set up so it's streaming a live feed over Wi-Fi to my laptop. I'll go ahead and switch over to my laptop and show you what that looks like. Okay, so here's what's happening on the laptop. This is a live view of the mask detection camera drawing detection boxes on people's faces as they walk by. It uses a YOLO V4 tiny model to identify faces and determine whether or not they are wearing a mask. The algorithm tracks faces across the frame and performs several inferences on the faces before voting if a face is masked or unmasked. It also counts the number of people and reports statistics to a remote web server on the overall percentage of people wearing masks. So this is at an airport where everyone's wearing masks. To test it on unmasked faces, I ran the algorithm on a video taken at a local gym where people aren't required to wear masks while working out. As you can see, it also handles unmasked faces. Next, I'll go over the hardware we used for MaskCam. MaskCam is based around the Jetson Nano, which is a system-on-module containing a CPU, GPU, and other processor peripherals. The Nano is hosted by a ConnectTech Photon carrier board, which has support hardware and various interfaces for connecting other components. MaskCam uses a Raspberry Pi HQ camera, which is connected over a ribbon cable to the carrier board. It also uses an Intel 8265 Wi-Fi module to provide a wireless internet connection. Optionally, MaskCam can also use a Quectel EM06 cellular module to connect to the internet if Wi-Fi is not available. Here's how MaskCam looks when all of the components are connected together. The availability of off-the-shelf hardware modules that are supported by the Nano allowed us to quickly develop this prototype. For a production version of MaskCam, we would design a custom carrier board that only has the interfaces and connectors we need for our application. Now, let's go over how the software works. MaskCam uses a video processing pipeline to grab frames from the camera, run inferencing on them, track and vote on faces, draw detection results, and output processed video. The code for MaskCam is written in Python and uses NVIDIA's DeepStream SDK to implement the video processing pipeline. DeepStream provides optimized functional blocks that use the GPU to speed up core image processing operations. MaskCam uses DeepStream to run YOLO V4 Tiny at 10 frames per second to detect faces in the incoming video. The overall video pipeline runs at 30 frames per second. The software also provides other features that run alongside the main detection algorithm. It reports detection statistics to a central server, allows users to live stream processed video, and provides a file server for saving and downloading videos. I'll show what else we can do on the laptop as the camera is running. The camera reports statistics on the number of people counted and wearing masks, and we've set up a cloud-based web server and browser interface that allows a user to view these statistics remotely. The front end has controls for interacting with the device, and it also has a graph showing the percentage of mask wearers and the number of masked and unmasked people counted over time. It allows the user to set the timescale so they can see the number of people detected per minute or per hour or per day, week, or month. It also saves video files to the device when interesting events occur, such as when a large group of unmasked individuals is detected. These videos can be downloaded and viewed remotely. The front end allows a user to select their camera from a list of cameras. I'm currently viewing the statistics from the Bozeman Airport 1 camera, but I could select any other camera that's been installed. The idea is for a user to be able to connect a lot of cameras to the internet and be able to quickly see statistics on overall mask usage in any given area. Our code on the Jetson Nano runs in a Docker container, which simplifies development and deployment. We're using a special operating system called Balena OS, which is designed to run containers. Balena OS allows us to view and interact with the device through an online interface called Balena Dashboard. The browser-based interface shows information about the device and provides a command terminal for remotely communicating with it. It lets us set up runtime configurations and also makes it easy to do over-the-air updates to the code running in the Docker container. All in all, our camera uses various software and hardware tools from NVIDIA and their partners that allow it to act as a connected smart device running machine learning algorithms on the edge. If you're interested in experimenting with it, the source code is free and open sourced under the MIT license. All you need is a $99 Jetson Nano developer kit and a USB webcam to try it out. You can get the code from our GitHub repository at the link shown here. Thanks for watching our demo.